Hello everybody. Our project this semester was Capture the Flag. In completing this project, we implemented a fully automated 4-on-4 game of Capture the Flag where each team was responsible for one set of the 4 rovers. While playing the game, each rover has a specific job and can only perform these tasks. The 4 rovers on each team consist of the Flag rover, the Sensor rover, and Defender rover, and the Countermeasure rover. The Flag rover's job is to navigate to the flag and capture it by bringing it out of the target flag area. The Sensor rover's job is to create a map by scanning the field while moving only in the designated sensor zone. The Defender rover is responsible for guarding the flag zone and tagging the other team's flag rover when it approaches. The Countermeasure rover is supposed to confuse the enemy team's tag rover and appear as the flag rover so that their rover does not know which one to tag. In working on this project, we divided each of the rovers up to different team members. Van was responsible for the countermeasure and GUI that controls all the rovers for testing and functionality to start the game and pause like timeouts. Timothy worked on the Sensor rover, Justin took on the Flag rover, and Daniel was in charge of the Defender rover. In each of the rovers, we had components that all of them had, one of which was the Wi-Fi. This is the source of how the rovers communicate. Each rover has this module and allows data to be streamed from the server, which is then relayed to a different rover. In our communication through the Wi-Fi, we had constructed JSON messages. Each JSON contained a sender key, a receiver key, message ID to track lost messages, and a data key, which contained the message we wanted to send. This is more difficult to implement initially, however, in the long run, it allowed for very easy testing and simulating via rover-to-rover communication, which could be done by sending a JSON message. Another component each rover shared was the motors. We implemented methods to allow for accurate movement and turns using the pulse width modulation. This allowed us to control speeds and accurately move with an error of 1 centimeter for distance and turn with an error of 2 degrees. The QTR8 line array sensors were another component that we used. We placed this component under our rovers to detect tape. For the most part, it was reliable. When the rovers crossed over a blue tape, we could detect sill. However, during the actual game, when crossing over extremely white tiles, it sometimes appeared to have similar readings as the tape, which caused it to recognize it as tape. Other than that, the line arrays were reliable for other tests that we had done.
So our rovers talk to the server, and the server can also talk to the client GUI. So the client GUI can also talk to the rovers. Our GUI is made with Java and JavaFX, and we use NetBeans IDE to create our GUI. Our GUI connects to a server using a button on the server tab. This GUI contains quick buttons to grab message statistics such as drop messages and buttons to contain the state of the game, so if the game has started or is paused. Our GUI also informs us when the Tiger rover has bumped into the Flag rover or anything else if the Tiger rover has incorrectly told us. The client GUI also displays the number of points the Tiger rover currently has, and it gets this through a JSON message. The GUI also contains 4 text boxes. One box is dedicated to displaying stats whenever a grab stats button is pressed. One box displays any messages sent by the GUI. One box shows any messages received by the GUI. And our separate thread on the GUI is always listening for incoming messages whenever the GUI starts up. And lastly, the master text box displays all messages sent and received by the GUI. Here we show that a screenshot of the GUI that shows various debug buttons to help us quickly troubleshoot an issue with our rovers or to simulate other rover actions by sending JSON messages to any rovers.
During this project, I worked on the Sensor rover. The Sensor rover is supposed to move only in the sensor zone and locate all obstacles and rovers and relay that to the team's rovers. In order to do this, there are IR sensors and ultrasonic sensors attached to the side to retrieve readings. IR sensors are designed to read in a straight line. These worked really well in half the range that they are supposed to work. Since we used a long-range 20 to 150 centimeter sensors, it gave good readings in the 20 to 185 range. These readings were accurate to 2 to 5 centimeters and could be done while moving. Reading past 85 centimeters could be read, but they would give increasingly inaccurate and could not be used for accurate map objects. The line array sensors were used to help the rover stay in boundaries, as moving out is an instant disqualification. When a tape is hit, the rover will move away from the tape and readjust. The line array also accounts for how many horizontal lines are crossed to determine which zone it is currently in, since no set measurements are given at the start of the game, so because of the varying game fields. The final sensor that was used was the ultrasonic sensor. The ultrasonic is extremely accurate for close and far distances. The only drawback is that it sees objects in a cone in the direction that it's facing, so although it can find objects, it doesn't know how big it is. Although the sensors were working and attached to the rovers, we could not find many instances to use it, as if there are two obstacles close to one another, there is no way of differentiating the two. As of the final demo, the sensor rover traverses the field indefinitely after it helps to orient and initialize all the other rovers. The readings were accurate to about 2 to 5 centimeters for all obstacles and rovers in both the x and y direction of the field. I believe that the sensors that we used were, although cheap and slightly inaccurate, they were fine for the purposes of the project. Something that we could have improved on was using a probability scan, which increases the probability of an obstacle being in a location after every sweep that it finds it in. This requires multiple sweeps of the field, but it combines multiple readings together, averaging it to find obstacles and rovers more accurately.
Hello, my name is Justin Liu, and I did the flag rover for Team 2. So, the flag rover was supposed to make its way to the enemy flag zone in order to capture the flag and score a win for us. Our flag rover was successfully able to orient itself upon initialization, and from there it would wait for additional information from the sensor rover. Using this additional information, once it was received, it would make its way to the enemy side, where it would locate the flag zone and trigger a flag capturing state, where it would take the flag out of its flag zone and score a win. One success we had in designing our flag rover was that we had a very efficient way of making it to the flag zone with a high degree of success. All we needed to do was make our way to the enemy far boundary, and from there it would turn accordingly or distinguish whether it already hit the flag zone and trigger the flag capturing state, where it would take out the flag. Something we could have improved on to increase our success with the flag rover was we could have used a different interface to retrieve information from the PixieCam. We used an analog output from the PixieCam to judge the location of our flag and find it, when we could have used a UART interface or the SPY interface in order to acquire the distance from the rover to the flag to more accurately grab it. However, this would be a small improvement since we had no trouble with getting the flag. Something else that we could have improved on was the robustness of all our design rovers, especially the flag. Since all the rovers relied on line sensors to find the line, it was highly dependent on the accuracy of these line sensors in order to get anywhere. We could have used a better algorithm to account for the value the line sensor would output in order to find the line, seeing as how that was an issue in the final demo. We also could have increased the robustness of our design by spending more time testing how to distinguish the flag zone lines from other lines. But once again, that would be a minor improvement on our design. And yes, our rover was pretty reliable. It would continue to run until it would either found the flag or completely left the zone, which we designed not to happen. Thank you. My name is Justin Liu, and that was the flag rover.
So the countermeasure is to obstruct the defender rover by bumping into it using the A-star search algorithm. But the reality for the final demo day is the countermeasure stands still to not affect the friendly flag rover. We wanted to do this because the limitations of having to orientate the friendly rovers and the sensors rovers limitations of telling which rover is which, so we couldn't know where the enemy flag rover is at all times, and we didn't actually want to block the friendly flag rover from moving or pathfinding. Another limitation includes detecting blue tape with the line array sensor. It was difficult on a black tile with bright white speckled dots. This means staying in the boundaries was difficult with the array sensor. The rover's movement was also not perfect. After any sort of turn or long distance straight movement, the rover eventually veered into another direction. Software-wise, it would think that the rover's at a particular point. Physically, the rover would be at a completely different point on the field. This rover can actually run forever and can keep receiving updates from the sensor rover since it's very basic. And one improvement that could have been done for this countermeasure rover is by using another line sensor. This would help detect blue tape and stay within the field's boundary. And another improvement is to keep the rover traversing properly, possibly by using a line following algorithm or have itself reorientate when necessary.
The tagger rover tasked to guard the flag zone. When the opponent flag rover tries to approach the flag, the tagger will try to tag it to make it return to its starting point. To find the enemy flag rover, the tagger uses maps from the sensor rover and perform an A-star pathfinding. When it reaches the target, the tagger uses bump sensor to tag it. However, the tagger sometimes cannot get to the target due to the limitation of motor movement. Therefore, on the final demonstration, the tagger only patrolled back and forth near the center zone. When the game starts, its orient after the friendly flag rover leaves the defense zone and then it starts patrolling. Due to the limitation of line following algorithm and line array sensor, the tagger did not move in a straight line all the time. However, the bump sensor worked correctly all the time, but it's only work when the tagger head directly to the opponent flag rover. The tagger can run forever and receive update from the sensor. One major improvement that could have been done is using better line sensor and using an accelerometer to detect bumping that would allow tag detection from all the direction.
Although we were able to get all of our rovers to the final demo, we could have improved on all the design of our rovers to increase our success with playing the game. We ended up having to make 2 rovers secondary and instead put all our focus on getting the sensor rover to work well with the flag rover, since we figured that if we won quicker than the rest of the teams, it would not matter if the other 2 rovers worked exceptionally well. This proved to be an okay decision, but we definitely could have spent more time with getting all the rovers to work well together and play the game in order to successfully have a high chance of success. Something else that we could have spent more time with was increasing the robustness of our design. We were able to successfully get the flag in ideal conditions, but it proved to be very vulnerable to less than ideal conditions, such as when the sensor rover would inaccurately hit a line when there wasn't one, and it would send inaccurate information to all the rest of the rovers, which would mess up pathfinding and flag capturing. All in all, though, it was a very successful demonstration of our design. We were able to get to the flag and capture it in the end. However, we were not able to rely on the sensor rover's data or any other rovers besides the flag. Thank you. That was Team 2's ECE 4534 Embedded Software Design presentation. Have a great day.